Hello and welcome to a quick video on the Haber process. So this is the first reaction, for the first main reaction that is involved in the chemical synthesis part of the Year 12 syllabus. Firstly, we're going to actually cover what the Haber process actually is. Secondly, we're going to use the framework that we built over in the video on Introduction to Chemical Syntheses, and we're going to be looking at some of the factors that affect the yield and the reaction rate of the Haber process. And finally, we're going to look at some important socioeconomic considerations that you have to make when justifying the Haber process in an exam scenario. So before we go any further, it's important to develop some context in regards to the Haber process. So basically, during the 19th century, especially during the times of World War I, the demand for nitrates, and especially ammonia, because it was heavily used in fertilizers as well as actually making some bombs, some nitrate-based bombs, and also feedstock, was increasing rapidly. The main source of the way in which we got nitrates was two things: niter, so N-I-T-E-R, and guano. And that was significant because guano is basically excrement, so animal excrements. So as you can imagine, we had two very ineffective methods for getting ammonia. And as demand for ammonia rise, these two sources could no longer meet the demand and could not supply fast enough. So some very clever German scientists came along and developed what we know as the Haber process. We'd actually tried to make ammonia from its constituents, nitrogen and hydrogen, for a very long time. This dates back all the way to the 1700s. So 1795 is when we first tried to put nitrogen and hydrogen to make ammonia, and we had lots of failed attempts. However, in 1908, Fritz Haber developed a method for synthesizing ammonia. And this is a really simple diagram that highlights this. We'll go into this in a lot more detail. So Haber actually came and made the method for how we theoretically could synthesize ammonia from its element. Carl Bosch put a real-life application into this process. So he took the theory that Haber made and applied some industrial principles and converted it into an industrial process. So that's the most important thing to understand. As I said previously, the Haber process involves making ammonia from its constituents, nitrogen and hydrogen, its constituent gases, that is. So notice how nitrogen and hydrogen are in a 1 to 3 ratio, and you make 2 moles of ammonia. It is also an exothermic reaction. That's the most important thing. And it's also good to memorize this number, especially in regards to exam answers, as it just shows you've done your research, done your study, and it's just good knowledge to have as well. And yeah, minus 92 kilojoules per mole is just a good number to know for exams. So now that we've understood what actually is the Haber process, especially when you're talking about exam answers and writing up those longer responses, it's first really important to understand why we actually need ammonia in the first place. Because you can only justify having a really schmick, kind of clean industrial process such as the Haber process if there is a high need for ammonia, which there actually is. So ammonia is actually used in a lot of things, and this first dot point is kind of the crux of it. So it's used in fertilizer, which is the most important thing. Also dyes, fibers, plastics, and explosives. So TNT, we use the nitrates present in ammonia. So TNT is a nitrate-based compound, and you can make TNT from ammonia. Also dynamite, it's important to add. So hopefully you can kind of see the Haber process was established in the 19th century during World War I, and we can make explosive with it. So hopefully you can see a kind of ethical consideration that's coming up, especially in regards to making explosives during the World War, right? Secondly, ammonia is really integral in making nylon or acrylic nylons, right? It's also used commonly in household cleaners and detergents. However, for an exam answer, if you were to remember anything, fertilizer, dyes, fibers, and plastics are the key. You could also state explosives such as TNT and dynamite. That's the main takeaway. So as we discussed in the video on the Introduction to Chemical Synthesis, there are some factors that affect chemical synthesis, mainly involving the availability of the reactants, the temperature, the catalyst that you use, and also the pressure. We're going to go over each of these individual factors and how they relate specifically with the Haber process. So firstly, with regards to the availability of the reactants. With regards to the availability of the reactants, the Haber process, as you may recall, has 2 main reactants. The first of which is nitrogen, and that's where we will start our discussion today. Lucky for us, the availability of nitrogen is very high because nitrogen has one of the highest concentrations of any gas in the atmosphere. Actually, the highest. It has a concentration of something like 78%. So the air is actually 78% nitrogen. It's actually a common misconception that you would genuinely think that most of the atmospheric air is oxygen because that's what we breathe in and out, but that's actually incorrect. It's mostly nitrogen. That's probably all you need to know with regards to answering a question in Year 12 chemistry. However, if you'd like the finer details of how we get the atmospheric air and get purified nitrogen, we actually use fractional distillation. So basically, we liquefy atmospheric air at a temperature of minus 200 degrees Celsius. Once we've liquefied it, we distill it, and then we can take out the trace elements or the trace gases, of carbon, oxygen, and some other trace gases, and get purified nitrogen gas. So fractional distillation is how we purify nitrogen gas from the atmosphere to use in the Haber process. So the next reactant that we need to have a conversation about is that of hydrogen. Unfortunately for us, hydrogen isn't as common as nitrogen in the air. So we need to do some chemistry in order to extract enough hydrogen in order for the Haber process to actually be worthwhile doing. We do this in a two-step process. The first reaction is one in which we react methane with steam that is of high temperature and also high pressure. So it tends to be anywhere between 3 to 25 bar. So very, very high pressure. This methane and this high pressure steam react to give us carbon monoxide and what we want, hydrogen. However, we run into a bit of a problem here. Carbon monoxide is potentially, if you like, could poison or destroy the iron catalyst or iron-based catalyst that we use in the actual Haber process reaction, right? Because if you can imagine, the nitrogen and hydrogen are all extracted in the same kind of plant and reaction vessel, right? So if we leave this carbon monoxide just in the reaction vessel, it's going to adversely affect this iron catalyst that is going to catalyze the reaction in the actual Haber process. So we need to do something with this carbon monoxide. Luckily, we can also react it with high temperature, high pressure steam. However, the catalyst this time is, so it's zinc, a mixture of zinc oxide and copper oxide, a metal lattice, that is, to give us carbon dioxide and hydrogen, more hydrogen. So we've made some hydrogen here. Those are the two reactions that we use to make hydrogen for the Haber process. And as a bonus, we've nullified the toxic effects of carbon monoxide and made carbon dioxide. So another factor that is really prevalent in any discussion on chemical synthesis is temperature. We went over this in the video on the introduction to chemical synthesis. So temperature can actually independently affect both the rate of reaction and the yield. So two very important things when it comes to chemical synthesis. We'll start with the rate of reaction. When you increase the temperature, you increase the average kinetic energy of the particles. So thus the particles are moving faster. So when they will collide and with more energy. So thus, if you increase the average kinetic energy, you increase not only how many particles are actually going to collide in the first place, so they're going to end up colliding more frequently, as well as they're going to carry more kinetic energy. So when they collide, they're more likely to have a successful collision because they'll surpass the activation energy because they'll collide with so much energy, right? So thus, an increase in temperature will increase the rate of reaction. However, let's take a look at the reaction for the actual Haber process. So as you can see by the enthalpy, it is an exothermic process. So I'll add plus heat on the end of that. With regards to yield, temperature can also affect it. If I increase the temperature, we'll stay consistent. Say I've increased the temperature to increase the reaction rate. So let's see how that's going to affect the yield. An increase in temperature is a disturbance in a system that is otherwise in equilibrium, right? With regards to Le Chatelier's principle, the system is going to react in a way to minimize the impact of the change that you've just imposed. So in this way, it's going to use some of that heat that you've introduced and shift from right to left, and thus decrease the yield, right? It wants to cool down, so it's going to shift from right to left by using some of the heat that you've introduced. Overall, this decreases the yield, and that is not what we want. So guys, that's something you need to highlight in your answers. You need to take the examiner through a stepwise discussion. So start with temperature, say that it affects both the rate of reaction and the yield. State why it affects the rate of reaction. So our conversation on kinetic energy, that's a really important or a good answer to write actually. Next, how does it affect the yield? Apply Le Chatelier's principle and show that it shifts from right to left. And this is a keyword. A compromise is reached between having a fast reaction rate and a favorable yield. They conducted this Haber process at many temperatures. So if you're at low temperatures, you have a really high yield, but a really crappy reaction rate. And at higher temperatures, you have the exact opposite. So you have a really high reaction rate and a really low yield. Overall, they found that the compromise or the sweet spot was between 400 to 500 degrees Celsius. You had a reasonably fast reaction rate and a reasonable yield. So this number is actually quite important for you to remember. Similarly, pressure is also something that can affect both the yield and the reaction rate. So we'll start with the reaction rate. An increase in pressure overall increases the reaction rate in gaseous molecules. So that is the creep. So increase the pressure for a reaction that is primarily involving gaseous molecules, you'll get an increase in reaction rate. This is because the molecules, you've reduced the overall space, so thus the gaseous molecules are closer together, and thus there's a greater chance of them colliding and reacting, right? So that's the first part. So an increase in pressure can also affect the yield. So say we increase the pressure, right? We've introduced a disturbance in the system that is otherwise in equilibrium. So if this is my reaction vessel, and I initially had that much space, now if I halve the volume by increasing the pressure, so always remember, an increase in pressure gives you a corresponding decrease in volume, right? I still have the same number of molecules, just in a tighter space. So thus, I've imposed a change in a system that's otherwise in equilibrium. With regards to Le Chatelier's principle, the equilibrium is going to resist that change by shifting in a way, or shifting in a side, or favoring a side that is going to minimize the impact of that change. For an increase in pressure, what this will look like is shifting to the side with the least number of molecules, right? So if I make this space as tight as possible, right, we have all these molecules in here, right? The equilibrium is obviously going to shift to the side that has the least number of molecules. So on the left side, we have 4 molecules, so 1 molecule of nitrogen, 3 moles of hydrogen. On the right, we have 2 moles of ammonia. So an increase in pressure is going to increase the yield and increase the reaction rate, which is kind of what we want. However, we have a bit of a problem. So typically an increase in the pressure is done through, you have your reaction vessel and you have a large cylinder, and basically you apply some sort of pneumatic pressure where this cylinder is going down, right? Although this is great in theory, right, an increase in pressure is detrimental, like a very high increase in pressure is detrimental for 2 reasons. Firstly, it's expensive because this pneumatic device is expensive to start off with, and to sustain that level of high pressure is really expensive. Also, it's dangerous. If you have really high pressure and things reacting at high temperatures as well, the chances of an explosion are really high. In an industrial setting, they found that a pressure of 250 atoms gives you an optimal increase in pressure that will increase both the reaction rate and the yield without the detrimental impacts of it being expensive as well as dangerous. Another thing that can affect any chemical synthesis is the use of a catalyst, and a catalyst is definitely something we use to make the Haber process overall more efficient. In the way of review, a catalyst is anything that lowers the activation energy. However, it does this by not participating in the reaction itself. So it is not consumed in the reaction at all. So overall, it lowers the activation energy and increases the reaction rate and allows us to get that increase in reaction rate by using a lower reaction temperature. So as you may have recalled, if we increase the temperature for the Haber process, we increase the reaction rate, but we decrease the yield, right? So we need a compromise, right? We can use a catalyst to otherwise kind of drop that temperature down. And if we drop that temperature down, we would, if we don't use a catalyst, we'd get a decrease in reaction rate, right? However, if we drop that temperature down, we get a bit of leeway if we use a catalyst. We're still preserving our reaction rate with the catalyst, and since we're dropping down in temperature, we're still preserving our yield. And thus, the catalyst allows us to maintain that fast reaction rate at lower reaction temperatures. That's the key here. With regards to the Haber process specifically, we use a catalyst that is called magnetite, so that's really important for you to remember. It's an iron-based catalyst, and something about magnetite is that it's ground quite finely, right? Over a bed, over multiple beds. You actually have multiple levels of catalyst, sometimes up to 4 in some plants, right? So they're kind of these iron-based magnetite beds that you stack one on top of another, and the nitrogen and hydrogen kind of just fall down and react, right? So that's the most important thing. It's ground finely to increase the surface area. So nitrogen and hydrogen are adsorbed onto the catalyst, not absorbed, adsorbed onto the catalyst and rearranged to form ammonia. So magnetite doesn't participate in the reaction directly, it indirectly participates by acting as a catalyst. So now we'll pull all of this together. So we have hydrogen that we've made through steam plus methane, and steam plus carbon monoxide that is a byproduct of the reaction with steam and methane. We have our nitrogen that we've sourced from fractional distillation, so I'll put frac distillation from atmosphere. So we get hopefully pretty purified hydrogen and pretty purified nitrogen entering our reactor, right? This reactor is set at 400 degrees Celsius and 250 atmospheres. So relatively high temperature, relatively high pressure, and we have a magnetite catalyst. And this is where the ingeniousness of the design really comes in. So we get some ammonia on this side, right? So the nitrogen and hydrogen react to make your ammonia. What happens next is kind of the genius of the process. We have a condenser here that you have coolant running in and out. This coolant serves to rapidly cool the condenser to about a temperature of about minus 70 degrees Celsius. This is obviously cool enough to liquefy the ammonia, so you get liquid ammonia as your key product, right? And this ammonia is swiftly tapped out and removed. So thus, I'll clear my, hopefully you get a snapshot of that. I'll clear it now. If we keep tapping ammonia out, we're decreasing the concentration of ammonia. If we then refeed the nitrogen hydrogen, as we're doing here, if we then refeed the nitrogen hydrogen back into the reactor, by tapping out the ammonia, we've introduced a disturbance to a system that was otherwise in equilibrium, right? So with regards to Le Chatelier's principle, if we can recycle the nitrogen hydrogen, the reaction will shift from left to right and make more ammonia for us. And thus, we increase the yield. Even with doing all of this, we get about 30% yield, or 30 to 35% yield achieved industrially, right? Otherwise, if we just did the reaction as it is, we would get a very, very, very tragic yield. And that matters very highly on an industrial scale. But that reactor or reactor mechanism is basically the crux of the Haber process. Another thing that we need to think about, especially with regards to the Haber process, is managing possible contaminants. The big one that you really need to highlight in your answers is oxygen. So the reaction or the reactor that I mentioned previously is a totally sealed system. So we try to limit the amount of oxygen that can enter the reaction vessel itself. As you can imagine, if we have oxygen and temperatures of about 450 degrees Celsius, so 400 to 450 degrees Celsius, and pressures of 250 atmospheres, we'd have a very, 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 very high likelihood for explosion, right? We also need to manage some other contaminants. So I'll clear my field. So the main ones are carbon monoxide, especially, which can damage the So it can damage the magnetite catalyst. And we have some secondary contaminants such as carbon dioxide and sulfur-containing compounds, which we especially get when we're purifying the methane. We didn't go over that process because it's kind of out of the scope of the Year 12 syllabus. However, you can get some sulfur-containing compounds as a byproduct of the Haber process, and you can get carbon dioxide, which overall, if we just leave them in the reaction vessel, will overall decrease the yield. So we need to get rid of them in order to not only maximize the yield, but also avoid poisoning the catalyst and damage the catalyst, which will also secondarily worsen the reaction as a whole. So this is a relatively high yield slide, summarizing the overall conditions involved in the Haber process, and it's really important to monitor these conditions to maximize both the yield and the reaction rate. One condition that we didn't go over is the ratio of the gases. We talked about how we purify these gases, but we didn't talk about the ratio that we actually add them in. It's really important, if we can, to add hydrogen to nitrogen in a 3:1 ratio, because that's the molar ratio that's present in the actual reaction. Why we do this is to avoid an excess of one reactant. So if we add too much nitrogen for given moles of hydrogen, we may get a excess or buildup in nitrogen, and that's going to slow down the reaction as a whole, right? Overall, we want a 3:1 ratio. That's the ideal. Lastly, to tie off any possible questions that you can get in Year 12, it's important to discuss some socio-economic issues. And there are three big ones to discuss when you're constructing an answer. One thing we'll discuss is the swap process. You can look into that if you're interested. However, in Year 12, they might ask for an alternative. This swap process is a possible alternative for the Haber process moving forward, to ensure that it's a more clean environmentally process. Because as you can imagine, we use a lot of methane, a lot of fuel fire, and a lot of fossil fuel to actually run the Haber process. So thus, the swap process could be a possibly more green, environmentally friendly process as an alternative. So there are a couple of problems with the Haber process. The first being the ecological impact of the product itself. So we use ammonia a lot to make fertilizers, right? However, nitrate fertilizers are actually soluble in water, and thus what happens is, especially in farmlands, if they're soluble in water and we use them a lot in soil, what happens is they collect in runoff waters or rivers. When they reach large bodies of water, such as a river or an ocean, a phenomenon known as eutrophication occurs. So this was going into the biology side of things. Essentially, what can happen is you get an unnatural growth of algae due to the increase in concentration of nitrogenous compounds in these large bodies of water, and you get a thickening of algae growth on top of the water, right? So if you can imagine, this is the land, and I'll change color. So this is the water. I'll draw it in green. If I have a high concentration of ammonia in this body of water, what will happen is the phenomenon of eutrophication occurs, and I get a thick layer of algae on top of this water, right? And that's bad for a lot of reasons, right? So it prevents sunlight from reaching, obviously, a lot of species that are emerged or actually have a habitat in this body of water, which ultimately detrimentally affects both the ecosystem as a whole for that body of water and any living things in it. Another thing that we briefly discussed previously is that the Haber process uses a lot of energy, right? So the recent article found that the Haber process actually is one of the most energy intensive chemical processes, using about 1 to 2% of the global energy consumption and producing about 1.44% of CO2 emissions. You don't really need to memorize these statistics, just know that it has these two detrimental effects. So it uses a significant quantity, so 1 to 2% of the global energy consumption just from one process. That is incredibly significant. And it also produces a significant amount of the CO2 emissions in the world, right? As well as nitrogenous-based fertilizers leaching into large bodies of water and causing the phenomenon of eutrophication, they can also leach into groundwater, drinking water, or normal drinking water to cause higher concentration of nitrates in both the drinking water and the groundwater to cause what we know as methemoglobinemia, right? And that is when, so you have Fe2 Fe2+ normally in the heme in your blood, and that is really effective at carrying oxygen. When you have this high concentration of nitrates in the drinking water, this has the potential to turn that Fe2+ into Fe3+, which is no longer that good at carrying oxygen in your blood. And that has a constellation of symptoms and overall is not that good for you, right? So it kind of depletes the amount of normal hemoglobin you have, and you have this really weird looking Fe3+ based hemoglobin molecule. And that is not good for you. So for these three reasons, these are the big socioeconomic issues. We can also touch on the fact that if you're struggling for an answer in a test, that the Haber process was produced during World War I, when Germany was at the war front and they needed a large amount of ammonia to produce fertilizer, dyes, etc. But also it helped them make TNT and dynamite in excessive amounts, right? And the Haber process was revolutionary because you went from getting ammonia from guano, which wasn't that effective, to this revolutionary industrial process where you could make lots of ammonia very quickly. So that's lots of bombs. So thus, that is a big social issue and a big ethical consideration that you will talk about in your Year 12 answers when answering these questions about the Haber process.